All right, so acid-base reactions involve the transfer of H+. Now, that's half of the story. There's other definitions that are used to describe acids and bases. There's what we call the Arrhenius definition. There's one that's called the Lewis definition. Did you guys lose my video? No? Okay. Okay, and then the one that we're talking about right here is called the Bronsted-Lowry definition. Okay, so we're always going to have an acid, which is any compound that contains an H, reacting with a base, which turns out to be anything that has a pair of electrons. Now, I know that's not something that we've talked about in this class yet, but if you're taking this class, that means you must have at least heard of lone pairs of electrons before you got here. Okay, and then in the course of the reaction, the proton gets transferred to the base, okay, leaving behind the rest of the acid. Okay, we have terms that we use to describe the products as well. So we have what's called the conjugate acid, and then the conjugate base. Okay, so common acids that you're going to see would be things like HCl. Hold on one second here. Okay, or maybe HNO3 or H2SO4. Our base could be things like hydroxide or ammonia. And there's other possibilities out there, but we're not going to get into all of them right now. Okay, so one thing that acids do commonly is they react with water. Okay, so if we take HCl and we dissolve that in water, what's going to happen is we're going to transfer that proton from the HCl to the water, which winds up giving the water a positive charge. And that new compound that we formed there, H3O+, is called the hydronium ion. Okay, and the positive charge on the hydronium ion is going to be balanced out by the negative charge on the conjugate base. In this case, that's chloride. Okay, now we've talked about different types of acids in terms of their strength, but also in terms of their proticity. So for example, we said HCl was a monoprotic acid. Whereas sulfuric acid would be a diprotic acid. Now, if I take sulfuric acid and I put that in water, we're going to form hydronium ion. Okay, and then the resulting conjugate base is going to be HSO4 minus. Okay, once that first proton has come off, that HSO4 minus bisulfate can then go on to react with water again to produce more hydronium ion plus sulfate. Okay, but we have to keep in mind that bisulfate is not a strong acid. Okay, so that is not a complete reaction. So we wind up with a little bit of the bisulfates not dissociating into hydronium. Okay. And then, and again, that was a diprotic acid. Okay, and then we could have triprotic, like what we saw with phosphoric acid. Now, phosphoric acid is a weak acid, so even that first proton coming off is going to be a weak or a partial dissociation. Okay, but then we can show that undergoing dissociation as well. Okay, and then the hydrogen phosphate can do the same thing. Okay, forming phosphate and hydronium. And again, that's our triprotic. Okay. So does anybody have any questions about proticity or the definitions of acids and bases or anything like that? Okay. Now, let's say that we have a reaction like HCl reacting with sodium hydroxide. Okay. Now, in order to predict the product of this reaction, it's helpful for us to look at this as if it were kind of like a metathesis reaction. I mean, if you figure H and Cl, H is, well, let's not go down that path. Let's try this differently. We know that HCl is the acid. Okay, so the sodium hydroxide must be the base. Okay, which means the HCl has to be giving its proton to the sodium hydroxide. But this is kind of troubling when you look at it because sodium hydroxide looks like it's all balanced out. Why would it want to take a proton? And it helps us to look at the ions that would be in solution. Okay, so if I put HCl in water, that's going to dissociate into protons plus chloride. Okay, and then the sodium hydroxide will dissociate into sodium cations plus hydroxide. So now we can kind of see where we can swap things out. Okay, so the H and the Na can swap places. So what we wind up with then is HOH, which is just a funny way of drawing water. Plus sodium chloride. Okay, we can show this in the net ionic form. Oh, sorry, just the ionic form first. So we get water, which does not dissociate to any appreciable extent. Okay, plus sodium chloride. So sodium and chloride ions. You can see here that chloride and sodium don't change. So the net ionic equation for this reaction is going to be H plus OH giving water. And this is what we call a neutralization. Which is a reaction that I've always found to be really fascinating, because if you had a solution of HCl and it got in your eyes, it would be terribly painful. If you had a solution of sodium hydroxide that got in your eyes, again, it would be terribly painful. But somehow when you mix these things together, you essentially wind up with eye drops. It's just amazing. Okay, so that's what that neutralization reaction looks like. Now, what's interesting here is if you see another reaction or a similar reaction, like nitric acid. Okay, so if we have nitric acid reacting with sodium hydroxide, okay, you can predict what the products are going to be. Okay, so the H and the OH come together to make water, and then the sodium and the nitrate. Okay, when we draw this out as our net ionic equation, or I should say the ionic equation as we approach the net ionic equation, we get protons and nitrate plus sodium cations plus hydroxide anions yielding water, which again does not dissociate to a very great degree in water, plus sodium cations plus nitrate. And again, we see that sodium and nitrate don't do much of anything here. And what we're left with is H plus OH minus yielding water, which should look familiar because these two net ionic equations are identical to one another. Okay, even though they refer back to two different reactions, the overall net effect is exactly the same. Okay, and this goes for any strong acid reacting with a strong base. Okay, so what I want for you guys to do is to explore the same exact reaction, but this time using HClO4 plus potassium hydroxide. So I want you to come up with the net ionic equation. And I'll give you guys a couple minutes to work on it before I start working behind you. Everybody doing okay so far? Any questions? Okay, again, you can see how we arrive back at the exact same spot as we did with all the others. Okay, does anybody have any questions? All right, let's move on to a different type of reaction. Okay, this brings us to redox reactions. Okay, so redox reactions sound pretty complicated, but they're not. These are all reactions that involve things changing their charges or the transfer of electrons. Okay, so for example, if you took HCl and you reacted that with zinc metal, you would wind up forming H2 and zinc chloride. Okay, now in this reaction, we have things changing their charges. Okay, clearly, when zinc's all by itself, it doesn't have any charge. But if it's involved in a bond with two chlorides, it must have its +2 charge. Okay, so we need to talk about how that's happening. All right, so the first thing that we're going to do is we're going to convert this to the net ionic equation because it's going to make things a little bit easier for us. So the HCl is going to break up into H plus and Cl minus. The zinc metal is not going to do anything. Neither is the H2. And then the zinc chloride, because it's soluble, can break up into zinc 2 plus +2 chlorides. Okay, so in order to have balanced this equation out, we would have needed to have a 2 in front of the HCl, which would have given us 2 H's and 2 Cl's. Okay, we can see that the 2 Cl's don't do anything during the course of the reaction. So we have 2H plus plus zinc yielding H2 plus Zn2 plus. Okay, now in this reaction, we have two processes taking place. We have something that's giving up electrons, and we have something that's accepting electrons. Okay, and that's the whole crux of every redox reaction, is there's always going to be something giving up electrons and something taking in electrons. And to understand what's exactly happening here, we need to break this reaction up into what we call half cells or half reactions, where we look at what's happening to each component. So for example, we can break up the reaction between two H pluses going to H2. Okay, from the reaction of zinc going to zinc 2 plus. Okay, so in order for zinc to become positive 2 charged, the only way that can happen is if you were to lose 2 electrons. So I'm going to show that happening here. Okay, now I know that we haven't gotten into bonding theory yet. Okay, but we know that H plus and H plus, in order for them to form a bond, there has to be electrons between them. Okay, because a hydrogen molecule is going to contain 2 electrons. Again, that's one of those things that you might remember back from the last time you took general chemistry. Okay, but anyway, we need 2 electrons to make this reaction happen. Okay, so you can see we have one side of the reaction picking up electrons and one giving up. Okay, so the one where we have something gaining electrons, we call the reduction. The one where we're losing electrons, we call oxidation. So there's a number of different ways of remembering this. Some people like to use oil rig. So oxidation is the loss of electrons. Reduction is the gaining of electrons. I've also seen people use, was it Leo Gurr? Same idea. So oxidation is the loss. Reduction is the gain. Okay. So how do we figure out the number of electrons that are being gained or lost without knowing about bonding theory, which we technically don't know about yet? Well, there's a way. And the best way to do it is to assign oxidation states. Okay. Now, oxidation states can be assigned to an atom based upon things like its charge and what it's bound to and all that sort of stuff. Okay, so there's a couple of rules when it comes to um, assigning oxidation numbers. Okay, first of all, anything in its elemental form has an oxidation number of 0. So, for example, if we were looking at solid iron, okay, that's iron in its elemental form, so it's going to have an oxidation number of 0. Okay, if I had O2, each one of those O2s would have a 0 oxidation state or oxidation number. Okay, the second rule is anything with a charge is going to be equal to the charge. So for example, if I had iron 2 plus, the oxidation number is +2. If I had chloride, the oxidation number is -1. Okay, and there's a couple of elements that commonly take on particular charges. For example, oxygen. Okay, oxygen is -2 unless it's bound to another oxygen. Okay, then it's -1. Now that does not apply to O2, but rather things like hydrogen peroxide. So if we look at potassium oxide, okay, clearly the oxygen has a -2 charge on it in order to balance out the potassiums. Okay, but if we were looking at something like hydrogen peroxide, okay, each one of those oxygens would be -1. Okay, hydrogen is +1 unless bound to a metal. Okay, and then in that case, it's -1. Okay, so if we're looking at HCl, in that case, it's +1. But if we're looking at sodium hydride, then it's -1. Okay, the fifth rule has to do with the halogens. Okay, so the halides are usually -1. Okay, and fluoride can only be -1. Okay, but chlorine, bromine, and iodine can take on others. Okay, so for example, in the case of sodium chloride, okay, chloride has that -1 oxidation number. But if we're talking about something like ClO, well, HClO3, in this particular case, it's going to be +7. Okay, and we'll get back into that later on. And then finally, the oxidation numbers of all atoms in a compound must add up to the overall charge on that compound. Okay, so We've actually already been using this line of thinking when we were naming things and that had transition metals. So, for example, if we had, let's do something simple first, FeCl3. Okay, we know that the chloride is going to be -1. Okay, we know that there's 3 of them. And we know that the entire molecule is neutral, okay, because we didn't put any charge on it to begin with. That means that the charge on the iron must have been +3. How do we know that? Because we knew that the charge on the iron plus the collective charge on the chlorides would have to add up to 0. All right, so let's see if we can look at some practice problems here. Let's look at the reaction of zinc with copper sulfate to produce zinc sulfate plus copper metal. Okay, so if we look at this reaction, the first thing we're going to do here is we're going to turn this into the net ionic equation. Okay, and that works out to look like this. Okay, so we can see that oops, that shouldn't be a +2, that should be a 0. Okay, so we can see we have 2 different half reactions that we can focus on. We have the zinc going to zinc 2 plus, and then we have the copper 2 plus going to the copper metal. Okay, so to figure out how many electrons are being transferred here, we just look at the change in oxidation number. Zinc is in its elemental form, so it's 0. Zinc 2 plus has a +2 charge, therefore its oxidation number is +2. Okay, so if zinc is going from 0 to +2, that means it must be losing 2 electrons, which means it's being oxidized. Okay, so copper with a 2 plus charge has an oxidation number of +2. Copper in its elemental form is 0. Okay, so clearly the copper is gaining electrons to become neutral, so that's going to require us to put the electrons on the reactant side, and therefore this is a reduction. Okay, so we can say that zinc is being oxidized, copper is being reduced. Now, the thing that kind of throws people off is there's another thing we can say here. Since copper is being reduced, okay, that means it is oxidizing the zinc. So we can say copper 2 plus is the the oxidizing agent. Okay, and we can say that zinc, because it's being oxidized, is the reducing agent. In other words, the thing that's being oxidized is doing the reducing. The thing that's being reduced is doing the oxidizing. And I know it's kind of a complicated thing to just hear and understand, but I trust you'll go back and read the text a little bit more, and that might clarify it for you a bit. But if not, of course, you can always contact me. Okay. So, are there any questions on how we assign oxidation numbers? Okay. And what's important to me here is that you be able to look at a reaction, break it up into the two half reactions, and identify what's being oxidized and what is being reduced. All right, so if there's no other questions here of that, let's take our next break. We'll start up again at about 20 of. And if you have any questions that you'd like me to go over when I come back, just put it in the chat, please.